How does the phase space look if A has complex eigenvalues? In that case, we first use a change of basis in order to get y prime equals c times y. Because in this new basis it is much easier to sketch the phase space. And once we have found the phase space for y, we can revert to the original variables to find the phase space for x. So how does this work? Usual setup, x prime equals a times x. We have found already a equals PCP inverse because we have a complex eigenvalue a plus bi. So we know that C is a scaling rotation matrix a minus b. And we know how to find p. It contains a real and minus imaginary part of our eigenvector v, which corresponds to lambda. So we have already done all of that. Now how do we then find the the phase space? First of all, we revert again to our y variable, so x prime equals a times x. Put the p inverse on the left, so we get p inverse times x prime equals c times p inverse times x. Again, choose y equals p inverse x, so we get y prime equals c times y. Okay, first we will do the y case. We know y of t equals e to the power ct times y0, some initial condition, and we know e to the power ct is also a scaling rotation matrix, but now with scaling factor e to the power at and a rotation matrix here, cosine, sine, and minus sine. So how is our phase space going to look in this case? So we take some example now to sketch it. Here we have an A, and we used this example earlier. We have this lambda minus 1 plus I and an eigenvector v. Now in this case, our small a equals minus 1 and our b equals plus 1. So what's going to happen? Now this rotation matrix is going to rotate whatever is going on. And the scaling factor e to the power at, we have a equals minus 1, so we have e to the power minus t. So this rotation factor is getting smaller and smaller. So if we start somewhere in the phase space, we are going to rotate, and we're going to get smaller and smaller, so we get closer and closer to the origin. Furthermore, our b is 1 is positive, so we are going to rotate with a positive angle, so we're going to rotate counterclockwise. So suppose we start somewhere here, and we are going to rotate, and we are going to rotate and get smaller and smaller. So there we go. And a point like this is called a spiral point. Now, that is in the y language. What's happening in the x language? Well, x is just p times y. So the y1 axis is now taken, the v1 axis is taking the role of the y1 axis, and the y2 axis is taking the role of the v2 axis. So in this case, we were rotating from y1, the positive y1 axis, to the positive y2 axis. So that's what's going to happen in our figure in the x space as well. And furthermore, we are going in. So here we are rotating from the positive v1 axis. You get the v1 and the v2 from the p matrix. We are rotating from the positive v1 axis to the positive v2 axis, so in that direction. So we are rotating again, and of course, due to the e to the power minus t, also getting smaller and smaller. So this looks something like this. So again, we get the spiral point, but do you notice the difference with the upper phase plane? And the upper one we were rotating counterclockwise, and here, in this case, in the original problem, we are rotating still inwards, but now we are rotating clockwise. So it can be a bit difficult to see whether you are rotating clockwise or counterclockwise. For that we have the following trick. Like take some random point, for example the point, let's take 2, 2. Then we know x prime equals a times x, and in 2, 2 we can compute a times 2, 2, we get 2 and then minus 8. So in the point 2, 2 we are going into the direction 2 minus 8, so like this. So that's telling you that if you're in the point to 2, which direction you're traveling, which is clearly in the clockwise direction. So how do you draw a phase space? Well, you need lambda equals a plus bi, and that's because you have a complex eigenvalue you're going to rotate, and the a in this case told you that you were getting smaller and smaller. Only problem can be whether you're going clockwise or counterclockwise. You can do this using this linear algebra argument with the different bases, or you can just plug in one point to see whether you're going, in this case, clockwise, or if you would have gone the other way around, counterclockwise. So that's how you can draw your phase space for x prime equals ax if a has complex eigenvalues.